Hello, everybody. It's Mrs. Pound, and I'm back with more from Chapter 4.1 on forces in motion. Today's topic is from Section 416 on forces in fluids. So, our objectives today are to compare the effects of compression on a solid, a liquid, and a gas, to identify the relationship of force, pressure, and area in a fluid, define Pascal's principle, and explain buoyant force. We've got a lot to do here, so let's get started. So, a fluid, first of all, is any substance that flows and takes the shape of its containers. Fluids include liquids and gases. So, in our picture here, I have water, and you can see the steam coming up here for the gas. So, those are both fluids. Now, let's talk about compression. As far as compression, solids, when you can try to compress them, they don't really compress very much unless it's something squishy like a Nerf ball that has a lot of air in it. But just a regular solid like a piece of wood, you're not going to be able to compress it. Liquids, you're going to be able to squeeze and compress a little bit, and they're going to go to other places. But gases, you can really compress those. In fact, we have things called air compressors that we use to compress uh, a lot of gas in a small volume and then put into things like our bicycle tires. And so, the reason our bicycle tires are not soft is because we have compressed the gas in there. We've gotten a lot more gas in there than can be in the air in a smaller volume. So when a gas is compressed, its volume is reduced and it applies a higher pressure, like in our tires. Now, we also have hydraulic devices that use this idea of being able to kind of compress that liquid and use it and transfer it to other places. This is a device that uses liquids to transfer pressure from one point to another. So, do you see all these pipes or hoses and everything on this equipment? That is because they are using hydraulic pressure to move the bucket in front of this machine. So, a formula that we need to know is for pressure, and that is pressure is force over area, or P equals F over A. And one application of this is that if the area over which a force is exerted increases, the pressure decreases. So I have a picture here of some flat shoes versus some heels. And maybe the ladies and have experienced this before where you can wear a pair of flat shoes and not poke through the ground or poke through anything, but you put heels on and that spike, that smaller area with the same amount of force will poke through the ground, will poke through soft ground, can actually damage flooring because it will poke through things. So, this is the idea where you have taken the same amount of force, maybe the same person wearing two different kinds of shoes. You decrease the area or you increase the area, and it changes the pressure. You decrease the area, you increase the pressure. You increase the area, you decrease the pressure. So, this is kind of the idea with when you see people laying on a bed of nails. Okay. If you just stand on it with one foot, that's really going to hurt, and those nails might go through your foot. But if you lay your whole body weight over that bed of nails, it will support you. It won't be the most comfortable, but the nails are not going to go through you. You can also walk over eggs this way as well. If you're wearing, say, flip flops, than if you are just on one toe. So you can actually walk over eggs as well. Now, Pascal's principle states that a change in pressure at any point in a fluid results in an equal change everywhere else in the fluid. This is how the hydraulics work. If we squeeze that bottle, okay, it changes the pressure and it will increase the pressure everywhere in that liquid. And so, what they do with hydraulics is they squeeze a small area and get a high pressure that then transfers to another area, and they're able to use that pressure change to use that force to move something like a large bucket on machinery. Now, let's also talk about buoyant force. This is the upward force exerted on objects in a fluid. This is what causes things to float, like this boat in the background picture, this little paper boat. Now, steel ships can float because you know that steel has a higher density than water, and we've always been taught that things with lower density than water float. So then why can a steel ship float? It's because the overall density of a ship is less than that of the solid steel because of the ship's volume is actually made up mostly of air. The weight of the water displaced is equal to the buoyant force exerted by the water on the ship. So the ship is made in such a shape that it is mostly air, and also its area is spread out over the surface of the water. If we just took the amount of steel in that ship and crumpled it all up, then it would sink. But we have spread it out so that there's a force from the water pushing up on the ship, and that it's really also a pressure thing. That pressure is spread out. And so the force from the water is able to hold up the ship because there's a lot more force because of the area over which it is spread. And so the force of the ship pushing down is equal to the water pushing up, and that ship will float. So you have to make it flat. It's a lot like the idea of a parachute as well with air resistance. If you don't have your parachute, there's not enough air resistance to hold you up, and you're going to continue plummeting to the earth very quickly. It's the same idea with the water that we have increased the surface area, and so the force from the water can then hold the ship up. So our objectives were to compare the effects of compression on a solid, a liquid, and a gas, to identify the relationship of force, pressure, and area in a liquid, define Pascal's principle, and explain buoyant force. So remember your 5 questions, and we'll be doing some demonstrations and things in class to clarify these different concepts.